welcome to our Talking Timber webinar. We are discussing a hot topic today, and we've got some great speakers with us today. A lot of these gentlemen like to set fire to things, so I'm sure we're in for a great session. So over to you, Brent.
Afternoon, everyone. So I'm just going to introduce the two speakers. Firstly, Prof Richard Walls. Richard is the head of the Fire Engineering Research Unit at Stellenbosch University, Africa's first research team with a focus on fire engineering and structural fire design. So Richard got his BSc Engineering Civil at University of Witwatersrand, where he was consistently the top undergraduate student while he was studying. And then he did a PhD at the University of Stellenbosch in fire engineering. His team has published the first technical guideline in the world for fire safety in informal settlements. He has contributed to publications by the World Bank, United Nations, and various other organizations, and he led the writing of South Africa's first infrastructure report card on fire safety infrastructure, which is being published in 2022. Okay, and then our second speaker will be Dirk Streicher. Dirk did his BSc and MSc in civil engineering at UCT. Then he spent 12 years as a civil engineer, mainly as a consulting engineer. And then since 1996, Dirk has been self-employed. He owns and manages a range of businesses and investments. And one of these is called Ignis Fire Testing. Dirk started Ignis as the only fire testing facility outside of Gauteng on the African continent. And he has conducted around 250 fire tests. The test lab does a range of tests, building primarily out of fire door testing. So those are our two speakers. I just want to draw your attention to the fact that Richard Walls, who's our first presenter, he's got an online course in timber and fire, and you will see on your screen the address for where you can find that course. It's CPD accredited by the SA Institute of Architects. So the website is thewoodapp.com. It's a website that's run by us at Stellenbosch University, and there's also several other wood design courses available, which you can have a look at. Okay, so over to you, Richard.
Okay, good afternoon, everyone. We're going to get started. Just pulling up my slides. Okay, welcome. Firstly, I apologize for my beautiful lighting. I'm sitting in load shedding, as I'm sure some of you probably are. So I'm going to be talking through fire safety engineering for timber structures, and going through a topic that as soon as you talk about timber, the issue of fire and fire resistance, fire ratings come up. So it's probably something many of you have had to deal with. And so just as an overview of what we're going to be looking at, we'll first understanding fire ratings, because sort of the first half of the talk is just to be, what is a fire rating? What are we actually trying to achieve? It doesn't matter what construction material we are using, but what is a fire rating? Then looking at different construction systems, but very, very briefly, just as a comparison, then to the focus designing timber for fire resistance, so we can put it all in context. So in terms of additional content, we have a YouTube page, Fire Sun, where various videos are available on testing and products and all sorts of things. So if you need additional content, you're welcome to go have a look at that on YouTube. And we've got fire safety engineering at Stellenbosch University. We've got master's and PhD programs, courses, short courses, structural fire, fire behavior, fire safety engineering. We do research, consulting, expert witness, R&D, etc. So now, as a background to this, if you want to get more details as well, a timber and fire textbook has recently been released free of charge. So free textbook on fire safety engineering for timber structures. This is many of the top experts in the world. So this is pretty much the who's who in structural fire and timber has published this book free of charge. And so you can go download that. So if you need any guidelines, but it's 486 pages of light bedtime reading. So a couple of slides that I'm going to give you today is a really, really fast introduction to a fairly detailed topic, but there are extensive guidelines being produced to help this issue. So firstly, I mean, my background is a structural engineer. And I know on these sorts of projects, as soon as you have timber, you have fire, the structural engineer says, well, that's not my job. Yeah, that's the fire engineer's job. But if we have a look at the codes and standards, when it comes to structural fire resistance, making sure the structure has sufficient resistance, the fire engineer is involved with that in terms of specifications. But our code that specifies what the structure has to do, SANS 10160, so this is the code of practice for structural design. This code specifies that we should design for accidental design situations, and accidental design situations include fire. So when a structural engineer signs off a building against SANS 10160, our loading code, which specifies winds and all everything, it actually has fire listed in there. So most structural engineers don't even know this, but they should be checking these structures for fire resistance. And it's considered what's called an accidental design situation, and a structure shall be designed for it, including exposure to fire. I'm not going to read everything else, but all you should realize is that our code of practice for designing buildings says, dear Mr. or Mrs. Structural Engineer, you should design for accidental design situations, including fire. Most structural engineers are not doing this, but it is actually a requirement of our code. And it's even listed under the accidental limit state. We normally design for what's called the ultimate limit state. This is the this is one of the ultimate limit states. And in the case of fire, the structural resistance shall be adequate. So it is a requirement. So fire resistance must be checked. The actions will be found in other codes. And then we've got our material standards. So we need to do it. It is a requirement. And this is how most structural engineers, when they see news like that. So as we go into it, firstly, now when it comes to building design, one of the key questions is what is failure? What is sufficient resistance? So if you saw a building like that and it had been exposed to a major fire, would you be happy or sad? Now, would that be acceptable? Would that be, hey, I've done a great job, or oh hell, I'm going to get my pantsuit off? Because accidental situations, what you're trying to do is make sure that the result is not disproportionate to the event. So you're actually allowed to have damage. If a fire breaks out and a fire spreads, you are allowed to have damage, even to the point of knocking the building down, possibly. But the issue is you're trying to make sure that no one dies, the neighboring buildings are kept safe, you keep the fire where it starts, you limit fire spread. So this would be a pass. This is fine in terms of structural resistance if your building looked like that. This is a steel building, that's similar situation for timber. But for instance, if this happens to your building now, the fire will spread if big gaps open up under walls. So that we've got to have a look at what is failure. And so there are a couple of criteria spelled out in the codes, our building code for fire 10400 part T, or the testing code 10177 part 2. We need to satisfy stability, strength, or structural resistance. So we've got to make sure everything can carry the load after a period of time. We also have to make sure that integrity is maintained. The passage of smoke and flame through the slab must be prevented, or wall, or whatever it is. So we must make sure, even if it's strong enough, if it cracks and flames and smoke pass through, it's a problem. Then also we have to make sure we satisfy insulation criteria. This limits the amount of heat that is allowed to pass through the slab or beam or whatever it is. The average temperature rise, the upper surface may not exceed 140 degrees Celsius. So even if you've got something that's strong enough and prevents flames from going through, for instance, steel sheeting, if it heats up too fast on the unexposed side, it fails. So we've got to make sure elements satisfy stability, integrity, insulation. Those are the three main requirements. And so that's what our stability or load-bearing requirements is. It strong enough? Integrity, is there a crack that the flames can pass through? And insulation, does it get too hot on the unexposed side? And so all of these you need to make sure you satisfy, depending on whether it's a wall or slab or beam or column. So now we have ways of testing that. And one of the things, one of the methods is what's called the standard fire curve. So that's this red line going up here. It's over 120 years old, and everything you hear in fire engineering is 30 minutes, 60 minutes, 90 minutes, 120 minutes. All of it is relative to this red line, and it's slightly arbitrary, this line. It's not a real fire. It's a benchmark. So it's useful. you run your furnace following this curve, but it doesn't actually mean that a 30-minute fire rating for a beam or column means it'll last 30 minutes in your building. It could fail after 20 minutes or 4 hours and still have a 30-minute rating. It's 30 minutes of a specific fire, and it's a bit of an arbitrary fire. So, you know, based kind of on the way that 3 guys could shovel coal into a furnace 120 years ago. There are other fires, the hydrocarbon and external, but the main one is the standard fire. And so this is how you test it. This is a furnace, this is at Ignis, and this is a door test. So you will see here that it was put in basically a furnace, a big box, burners at the side are pumping in hot gases, and it's exposed to it. And then you see, so that would be an integrity and insulation failure. The smoke and flames are coming through. It's heating up on an exposed surface, and so this would be a failure. And you could put in a wall panel, a bigger wall panel. You could put in columns or beams inside the furnace, and you use this to assess how long does a sample last. Does it obtain a sufficient fire rating? There are ways of calculating it, which I'll show you soon, but that's what we're trying to make sure that a certain amount of time is satisfied for that. Because as I said, it is different. A real fire has growth, flashover, fully developed decay. It doesn't go through that. So it's a bit of an arbitrary curve. And normally what we are trying to make sure is that time to escape is actually before your structure is damaged. There's ignition, and then the fire slowly started growing. This here is where you want to get people out the building. So if you've got 5 or 10 minutes, this is to get people out. It's not how strong the structure is. At this stage, the structure doesn't even know there's a fire there because it's not hot enough. The standard fire curve is kind of after it's fairly well developed. That's sort of what it's mapping out, the standard fire, that dotted red line. So now let's have a look in comparison. What do other materials do? So now, for instance, different products you will typically protect. You may protect it with an intumescent paint. For instance, this is a paint and it swells and it provides a char layer. And then you would put this around steel or sometimes even concrete, sometimes timber. I'm a little cautious on the timber, but it can be done. And you use this to protect the material and give you extra time, additional fire rating. But this stuff is expensive. Sometimes, for instance, these are different column sizes. This is the cost of the steel. This is the cost of a fire rating for 1 hour, and this is a cost of a fire rating for 2 hours. So sometimes the paint can cost more than the steel. So fire protection can be very expensive, and you need to specify it correctly, irrespective of what product you use. But so for something like steel, you put something on to protect it. Steel heats up very quickly. And so what happens is around 400 degrees Celsius, it starts losing strength. So the red line is strength. It's going on 100% of strength, then it starts rapidly dropping. At round about 550 degrees Celsius, you've lost about half your strength. That's sort of often quoted as a critical temperature. It's not a magic number. It doesn't mean the building suddenly falls down at 550. It's kind of normally around then your resistance exceeds your capacity, around somewhere between 500 and 600 degrees Celsius based on the lost strength. So that's what you're trying to prevent. Concrete as well. Concrete normally survives well, and I'm doing this so you can then look at timber in comparison. But failures do happen. This is a concrete column that has failed. And what happens is for instance, there was a big compartment, fire broke out. We're looking at this column, and it expanded. The fire heated the element, and it actually sheared the column through. So you've got a 500 mil by 500 column. This is big, lots of rebar in there. The thermal expansion actually is what killed your structure. It actually cut through that column. So different structures fail in different ways. And the thing is with timber, it doesn't heat like steel does. It's not thin. And it doesn't expand like concrete does. It's a different way we design. And also one thing, concrete is normally assumed to be safe, but you can't necessarily always assume it to be safe, especially with modern products. If you've got high performance concrete, this is concrete blowing up, or if you have post tensioning, various other things, you've got to be a little bit careful with your fire resistances. So now let's get into timber. So I mean, you guys now are all probably timber experts, and so we've had this big drive to use timber and timber high-rise buildings. One of the biggest challenges to the use of biomass in construction is fire safety. It's a major headache. I mean, I understand obviously the durability issues and moisture, etc. In terms of approvals, the fire department has a heart attack. You go and say, hey, Chief, can I build a 10-story timber building in downtown Cape Town or Sandton? The fire chief is going to have a heart attack, probably. But it's being done around the world, and how? What do we need to look at and what makes it safe? So, I mean, here you can see we're going 18 stories and above in mass timber. So it's, lovely materials, etc. But the fire engineering design becomes key. It's not an add-on at the end. Gee, let's slap some paint on this thing and it's done. Fire safety is a key component in design consideration from the start to get to these sorts of final products. And so there's various things you have to think about, and you've got to look at it holistically: your detection, your suppression, your durability, exposure, etc., etc. So I'm just borrowing some slides from my student. He actually is about to graduate with PhD. We've got a couple of people, Darren Solon, Marika Duplessis, and then another MOS student, Sipapelo. They're coming through. They're doing postgraduate studies in timber and fire. So we've got a nice strong team doing this work. And when it comes to structural fire, you've got your low-story, low-rise buildings. You've got your post and beam, low-rise, single-story, multi-story, and mass timber, large solid wood panels, walls, floors, roofs. So this is the sort of area where structural fire really gets involved and design. Most of these sorts of systems, you're looking at cladding. You put boards on. You basically protect the timber. You make sure the timber doesn't get exposed to the fire, and then you keep it safe that way. With mass timber, we may leave it unexposed. So this is our timber. Yeah, to some extent you do it there, but whenever you have light timber, you clad it. When you've got heavy timber, you can start looking at charring and design. So this is what you get. This is a tester. It was done by David Barber from Arup. There's various tests being done around the world. We've got testing on the go. So big beam, slab, etc., popped into a furnace and then exposed to fire conditions. So that's the column before, column after, beam before, beam after. And you'll see that material has been lost. So material is gone. This is, I think this is the column here, but you'll see there is a residual cross section. There's material that's left over that can still carry load, and we are relying on this middle section to give us the strength. Yes, we've lost timber on the outside. Yes, we may have to strengthen the structure. Yep, it's burned. But if we've done it, it can still be strong enough, because what happens is if you've got a little block of timber, there's your residual mass, there's your temperature. It's going on. First, it dehydrates, so the moisture starts coming out of it, and then it starts having pyrolysis and basically combustion, producing gases which can burn. So then you start getting flaming, and then you've got char oxidation. We are relying on this oxidation layer, the char that forms, to protect our structure. So how does this affect the strength of the structure? How does it affect the compartment fire dynamics? So is it strong enough, and what happens? So here is some layers of timber. Here's the fire from below, and now it chars. We have now a reduced cross section. There's a char in front. And so if you look at the temperature through the section, you've got charred and then an heated but uncharred, and then remaining residual section. So we assume everything hotter than 300 degrees Celsius has lost its strength, and then there's a transition, and then, okay, it's got its full strength. So we design for that. We lose the char, we lose our heated layer, but hey, so I'm not going to go through this, this example in depth, but I just want to show you that there are engineering methods you can use. So for instance, a glulam beam, which is produced from SA pine, is used in a building. It's 130 mil wide, 720 mil deep. It's exposed to fire from 3 sides. After 1 hour of fire exposure, what are the remaining dimensions? What are the remaining dimensions can be used for structural calculations? And so you need to know how fast does that char front move, and it's dependent upon the species. And then what is left over? So for instance, there's some details you go through, you'll pull this up, you find out I lose that char layer, I've got a heated layer, and you have a residual section that you designed for at the end. You go through the calcs, etc., etc. and you end up with that section in the middle. And one thing that happens is in the fire limit state, you design for lower loads. So for most buildings, you design for the worst event in 50 years. You're now moving offices and you chuck everything in the corner, you pile it high, and it's as high loads as you can get. So it's the worst short-lived event in 50 years, where for fire, the chance of that worst event in 50 years happening at the same time as fire is very low. So often your design loads can be half. So even if you have lost strength, it doesn't need to be as strong because it's being designed for a lighter event. So you lose material, you've got a lighter event, maybe you need a little bit extra timber, maybe you don't, but you have a residual cross-section that can carry the load. You do have to, however, be careful though, especially when using engineered timber, because you can find char fall-off. You've got layers that are stuck together. Some adhesives are better than others. So for instance, this is SA pine. We've done testing with SA pine and this is both pictures of SA pine, but we also did eucalyptus. And so you can see then how it chars, then gaps open up, the fire penetrates through, and eventually it'll get through. But we got basically an hour fire rating on some of these samples. I think we even got close to 90 minutes on the eucalyptus. So there is work that's been done to look at what is the fire resistance of these systems, and can you get it? But yes, the timber is charring. So the real danger, though, and this is something you should think carefully about, is you can design that timber to work. You can make sure you provide some extra char, it works, but the real danger is your connection. If you look at buildings around the world where real fires have occurred, buildings don't collapse because the fire resistance was 61 minutes and it should have been 75 or 90. Buildings fall down because of connections. Connections are always, or almost always, the first thing that goes. So in a real fire, when things start moving around and get hot, it's these connections that fail. And this is where you need to be careful and make sure those connections are protected. So for instance, this work, they put an intumescent sealant, that sealant I showed earlier that expands. And so if the fire tried to penetrate into that joint, you block it. There are some guidelines in the different documents, but you want to make sure these are safe. You want to protect these to put everything together. And this is where it's the same thing even in timber trusses. A timber truss, you get a little bit of resistance of the timber members, but what fails in the trusses is those gang nails, the connectors. Those will give you a couple of minutes because they steel, they heat up, they char, they pop off. So you will maybe have a 3-minute or 5-minute fire rate on a timber truss, where the timber itself, it's the steel that fails before the timber, or where the steel's anchored. So you want to make sure that this section at the end of the day holds out, and put some time and effort into engineering that. And then another thing that is starting to now come into codes, and this is a topic of ongoing research, is that, for instance, in a normal building, let's say you require 60-minute fire rating. That is based upon fuel loads. How much fuel is in the building and how fast will it burn? But when there's timber, the skeleton of the building, the beams, the columns, the slabs, etc., contribute to the fuel load. So you also have to start asking, is a 60-minute rating now suitable? Do you need to increase the fuel load in the building? Now do you need to design for a 90-minute fire rating? Or what some codes recommend is they say you have to clad a certain percentage of the columns and beams. And that's to reduce the energy being released, to reduce the intensity. So yeah, you can have timber, you can have some exposed timber, but you can't have 100% exposed timber. You end up requiring a certain amount of cladding to it just to reduce that, the maximum heat release rate, how fast it burns. So these are things to think about, and those are the sort of things that go into these high-rise engineered buildings around the world. So just a couple of final notes. I've been through quite a lot in quite a short short period of time. So fire ratings can be obtained, but charring is key. You're designing for material loss. For steel, you're protecting it. For concrete, you're insulating it with cover. For timber, you're designing for char. It doesn't expand. It doesn't move so much as the other materials do. But you lose material and you would have to replace this. But normally fires are so rare that you do accept, all right, I'd have to replace some material. Timber chars at a predictable rate, so you know it'll be there. You know it will provide a certain resistance. It's a robust thing. However, connections are the most likely reason for failure and collapse. Doesn't matter what type of construction system you're using, connections are always key. When a building falls down, it's most of the times the connection or near your connection where failure occurs. So these are things you have to look at. And then heat release rates and fire intensity increases due to the presence of exposed timber. Some codes limit the exposed area of timber, so guidelines are currently being produced. There are various organizations that are sponsoring, like ARIP, sponsoring large-scale fire tests and others to try and understand it. Now, fire departments are not going to love you initially. It's not a well understood material, and you must understand fire departments are quite cautious. They don't want to approve something that they think may be a risk. So there will be a series of engagements in the coming years. There's definitely a movement. I'm definitely picking up a greater willingness to allow it, and there have been some projects that appear to getting greater levels of positive feedback. But this is something that you will need to have your fire engineer and your structural engineer engage with the fire department early on to make sure that it's approved. Unfortunately, the quality of fire services range. Some are very proactive, up to speed, knowledgeable, and innovative, so they'll work with you. Others like, no, the code doesn't say this, so tough luck. So then there may be a more difficult process. It depends on where in the country. So yeah, so those are just some thoughts to think about. And just taking you through firstly then how does fire resistance work? And then we had the furnace testing, making sure we design for it. And so yeah, so that takes me to the end of my discussion. We've tried to leave a bit of time, but at this stage we're going to swap now to Dirk Streicher, runs Ignis Testing. He is going to be coming on. So Dirk, you there?
Yes, I'm here.
Okay. So do you want me to leave my screen displayed, or is there anything you want to put up?
That's fine. You can leave it there.
Okay, great. I do have the cone picture if you need. I can go there with as and when needed.
Thank you very much. Yes, I think, Richard, you've told us so much so that I'm wondering, it's like the guy went to court because his bakkie was stolen, and at the end he said the attorney was so rough on him when he left the courtroom, he wasn't even sure if he had a bakkie. So, but I think we must cut it piece by piece. So, but one thing I think we can say is that we are all experts in wood and fire because we all have attended a braai, and you look at the flames and you suddenly realize that different wood give different energies because you braai differently, different results from them. But what is happening? And that is a question that we have to answer, and that is why we do testing, and that is why we are here, and not only to test whether the material or the assembly passes 1 hour or how many hours you want, but also to investigate and try and understand what happens with intumescence in timber, what happens with treatment. And one thing I've learned with testing is that most of the time it's an attention to detail, attention to joints, attention to rebates, to how you fit stuff, more than the material itself, perhaps. But after we've done all this, I think of what my hydraulic professor said. Once you start looking and learning and seeing what timber does in fire, it's like he said, between shooting and streaming flow, when you look at a river again, you will never look at it the same way. So after we've been involved in timber and fire, I think you will never look at a fire the same way again. And that opens a whole book of what and how can we improve timber for fire safety. And one thing came to my mind is that if people think about fire, about timber in construction, they always think about, but it's a fire risk. It might be, but it might not be as bad as most other materials, especially nowadays, the composite materials and your polycarbonates. And we know that different materials give different results. So we have to find out what is best. And one thing we know about timber is that it is the earliest structural material ever used, and later, centuries later, we still use it, and it's still one of the best materials available, with properties that is hardly met by any other material, especially in timber construction. And I can give you examples of where timber is excelling most other materials, even steel. It is what we use in formwork and scaffolding. Is called a GTX beam. It's a 150 millimeter by 63 millimeter beam. And we have tried to replace that with steel, with composites, to come to the conclusion that timber is still by far the best material to use for that size beam. So there are cases where timber is just better than any other material. So the question is, so what? Well, my answer is to find out what is the real fire behavior property, so that we can design structures incorporating timber and still have a safe building with respect to fire behavior. So how do we do that? We must go into calorimetry of the material and understand the behavior of the material. This will immediately force us to use physical properties such as energy in joules, power in watts, heat flux in kilowatt per square meter, and the reaction to the three modes of heat transfer. And temperature on its own is not enough, and 0 degrees Celsius is not zero anymore. This is where apparatus such as a cone calorimeter that you see there comes into play, and will, for the time being, the only real bench test around to produce the required results. With that piece of equipment, how simple it might look, if you look at it, it's quite involved in terms of the chemistry, the physics, the measurement of your oxygen depletion, and to get to the final results. But we do get very good results out of that, and we will show you a graph later. There it is, and that graph, if you really interpret that graph that you see there for different materials and timber, and what treatment you've given timber, that can really give a lot of information, more than one has ever thought, from a graph as simple as that. Or, well, it looks simple, it's not that simple, but you can get a lot of information from that graph, and that makes you think. And if you look at the heat release rate there in kilowatt per square meter, for instance, for that material, say even for timber going up to 200 kilowatt per square meter, then if a door face starts to flame, which is 2 square meters, you suddenly sit with a 400 kilowatt of power, which is quite a lot. And that is, if you do fire testing, you will realize when a door skin sets alight, how much the temperature in a furnace increases, sometimes at such a rate that you have to switch off all the burners. So what have we learned so far? Well, one thing I've learned is that Intumescent is not the golden product, especially the bottom of horizontal surfaces such as on mezzanine floors, because it detaches and it falls off, although it might intumesce quite well. So we will have to start looking for different, I would say, a different approach maybe to timber protection in terms of fire resistance. And it was, Richard mentioned about roof structures, where the timber itself might, if it's only timber in a roof structure, might give you a good 1 hour resistance. But when the plate, the gang plates comes out, and we've done some tests on that, you lose all integrity or structural strength within 5 minutes, you can have the roof on the floor. I know there's a school of thought that says, but the risk of roofs falling down is not that high for the people inside. Well, then the next question would be, if that is the case, why do we have 1 hour rated doors within top floors if the roof can come down within a few minutes? So we'll have to rethink the risk of roofs in building structures again, and I think that would put a lot of research back into the gangplank and how we do have to connect these timber members. As I said, in future research, my view is that we will have to look to something like similar to a CCA product that we can impregnate the timber with and get to resist flaming. If we can resist early flaming in timber, I think we can go to a winning type of product or way of preventing sudden high energy or heat release or heat flux in timber structures. The problem with that is not only the structure itself, but if you have a sudden high heat flux release, you set alight other products in the building that might not have ignited at a lower heat rate and contributing to the total load, fire load. To conclude, I don't know where the secret completely is in timber, but I know that we must not stop searching. And it is for this reason that I think we have to thank people like Prof Walls and Prof Wessels for initiating this research into timber and timber fire, and we would appreciate any contribution to this field and to the support of fire resistance and how to do it, and also that we have to initiate perhaps more testing, more I would just say pure thinking about timber and fire in structures. So yes, Richard, I think the industry must be highly appreciative of the action you took about 6 years ago with your engineering, the fire engineering research unit, and the way that we could have assisted you with tests and hopefully in future do more tests and also get improved test methods to enhance timber, and not only timber, but all fire flammable materials in structures in future.
Thank you, Dirk. All right, so ladies, we're going to go to time of questions now. So thanks. Firstly, I see Michael Kluis. Michael, how are you doing? It's an old student of mine. He's now a consultant in timbering industry. So a couple of questions he's posed. Can Intumescent be applied on timber? Can it? Yes. Does it work? That's the second question. The effectiveness of the products varies. I haven't been involved in enough testing to categorically say no or yes. I am cautious of it for a number of reasons. So I would caution you just to take an Intumescent, because if you see, for instance, what's happening here, it takes a period of time for the Intumescent to activate. If by that stage the timber on the back is starting to char, this actually could peel off and fall off. So you'd want to make sure that the Intumescent has been tested and what it's saying. So you really want to get hold of the material. If you put enough of it on and it stays bonded, then it will provide additional resistance. Yes, I mean, that's its job. The big thing is, does it stay bonded? And also, could the chemistry of the burning timber influence the Intumescent? So I don't have categorical answers to those. I haven't looked in depth at the latest and greatest. Is it that the textbook I showed you earlier, hopefully they've got the latest results. Where's it gone now? Go get hold of it, it's free. So have a look through. Do residential buildings in South Africa require a structural fire rating? You will find that there is a minimum rating. Roofs, not really. The new version of 10400 Part T is badly worded, in my opinion. I'm on the committee, but hey, it's a bit misleading. So roofs, you can kind of get away without the fire rating, but especially your boundary walls, your compartment walls, walls between, for instance, your garage and the rest of the house. There are certain ratings required of sections of your house. Yeah, especially you said do. So you'd have to go through and check, but no, it's not necessarily every single element. Often, most roofs in the country are not fire rated. Every timber truss with gang nails is not, or with connector plates is not fire rated. But the same thing, all light steel frame structures, all steel. I mean, steel heats up and fails in 8 to 10 minutes. The light steel trusses. So just because it's not combustible doesn't mean it's not fire. I mean, it's fire rated. So most roofs do not have, and you'll find that discussed at the bottom. I think it's table 5 and SANS 10400 Part T. And then could you elaborate on which types of glues have been shown to perform better or worse in fires? Depends. Look at the glue and it. So your polyurea, polyurethane. Sorry, the glue expert Brandt just cringed as I said that. We even were testing with him. So there's been testing Brandt's been involved with recently. That tends to melt, and there are other ones that are available. So you'd have to have a look. But the polyurethane is it's easier to work with, so liked. Brandt, I don't know if you want to jump in and anything for you. We haven't discussed your final results, but anything you want to add there? There are various glues available, though.
Yeah, Michael. So the two that we tested was polyurethane, which is, I think, mostly used in, or some engineered products quite popular, like CLT. And MUF was the other adhesive, and the MUF definitely performed better than the polyurethane.
There are others that are recommended. You'll see in these guidelines, there's various guidelines that are suggested to enhance fire ratings. Okay, any other questions? While the questions are coming through, you're more than welcome to shout. I just want to point to something just to make clear, just looking where I put it in my slides. This here, because one of the things that people often worry about or misunderstand is you get different types of tests. So for instance, a material can burn and a material can release smoke and gas. That normally is a greater concern in the sort of smoking and flaming and fire spread in this initial phase. We're trying to get people out the building. So you can have a material that flames plenty and can reduce your evacuation time, but you can get a fire resistance. You've got two separate types of tests. One is, what does it contribute to the flame spread? And timber actually doesn't flame that easily. It's actually has very low flame spread. I mean, synthetics, they're all oil-based. I mean, your curtains and nylons, they spread like hell. So you've got your reaction to fire, which kind of gets the early bit, and then you've got your fire resistance. So your fire resistance is how long does a piece of construction material survive in a furnace test. So that's what your standard fire resistance test is looking at. It doesn't matter if it burns or not, if it releases energy or not. You're comparing it against a benchmark and how long it satisfies integrity, structural resistance, integrity, insulation requirements. Brandt, you'd like to say something there?
Richard, maybe, I'm not sure whether you or Dirk will be the best to answer that, but I was thinking now, you both commented on roof trusses that might, not be fire rated. If you use wood trusses and the small nail plates are the problem, would something like normal nails or bolts be a better option? I don't know if you've tested stuff like that, maybe, Dirk?
Brandt, by experience, if one goes back to the past where roof trusses were nailed together, that that is still, I suppose, one of the best bonds. But in terms of modern day design packages, the way they do it, and of course the ease of construction, that the fact that you have an inline structure with the plates, I don't think that will go out, but one will have to maybe consider a nail through the plate, or the plates in both members of that joins a plate. So yeah, I think that would be, I suppose, the best consideration to do. But I suppose we don't want to go back to overlapping and have 3, 4, 5 nails through it. But that is still a very good joint.
I think one of the points also is, do we need a fire rating on a roof? Mostly not. Mostly, if the roof collapses, it actually provides a vent and the flames go up rather than to the rest of the house. So it's not, roof failure is not necessarily the end of the world. It may actually be a good thing. And normally your roof is supporting thin steel and other things. So normally your sheeting and your tiles and everything else has failed long before you as well. So can it be a problem? Can you enhance it? Yes. Also, it depends on what you're doing. One of the problems, once again, with connections, if you've got something that's steel, it's got a very high conductivity. So it sucks the heat down it, conducts it in, and then it chars it in adjacent to it. So you have to look reasonably carefully at your connections. If you have a roof structure that requires a significant fire rating, then you do actually need to start thinking quite carefully, either at going to mass timber, or protecting it, boarding it off, doing something. Especially if it normally requires 30 minutes, 60 minutes, but it doesn't really matter by that stage. All the materials you have to start thinking about, a little bit of design. Concrete, as I said, fairly robust, but that adds on a lot of cost. Normally, if you're going to start making concrete slabs on top of every home. So then I see there's a question here from Samantha from Bram de Villiers. Products like wood safe, does it work? How does it work? I personally am not familiar with wood safe. Dirk, have you been involved in testing? And I see Darren, he's our PhD student. I'll just hand over to him. Dirk, you want to comment? Darren, if you want to talk, you can, otherwise we'll type an answer.
We did do some tests with wood safe and a number of other products. One comment I can make in terms of referring mostly to doors, it's never the core itself that's a problem. It is usually the detail around it, around your rebates, your locks, that is a problem. It's hardly ever that I see a problem with insulation, for instance, and even integrity if it burns through the rebate. So there's a lot of, I would say, effort that must go into attention to detail of design than only in surfaces. But to add to a comment you made about flame spread, the first test we've done in the SBI, the single burning item, we had some veneered sheets lying around, particle board sheets with veneer on, and we saw no flame spread on that, nothing.
Sorry, Darren, do you want to make a comment and then we'll get... Sorry.
Darren, you are able to answer the question?
Yeah, do you want to make a comment?
Yeah, my main comment is products like that mainly deal with reaction to fire. So like Dirk said, it'll help you with flaming, but it's not going to change your structural fire resistance.
This is the issue there. Darren's he's just wrapping up his PhD in structural fire. So that's what I've been pointing out. It depends on the product, but it could be a product with sort of, you've got various salts or silicates, etc., and it impregnates into the wood and it reduces the combustion reaction. So it doesn't make it non-combustible. I've seen some videos and like, hey, timber doesn't burn anymore if you put on this stuff. I'm like, yeah, okay, I'll believe it when I see it. You're reducing the ignition, you're increasing the critical heat flux, but if you put it in a furnace for long enough, it's still going to burn through. But you're reducing the rate that pyrolysis gases come off of it, reducing flame spread, etc. But once again, as Darren pointed out, you're in the early phase here, rather than getting a structural resistance. Maybe it'll add on a couple of minutes, but yeah. Okay, then Mark Rohan O'Connor. After a timber post or beam has been exposed to fire, I have seen, oh, sorry, it's jumped. I've seen cases overseas where the charred elements are cut away and affected area replaced with new timber. What is your view in this practice in terms of reinstating the fire resistance structural strength of the timber element? Now, normally in structural fire engineering and structural engineering in general, yes, you can reinstate sections with other material. Typically, your biggest problem is how you link them together. So how do you join them? So for instance, at the end, if they are taking a compression load, my one fist against the other fist, if there's a little bit of a gap, it's not transmitting load from one to the other. You've got to make sure you seal up all the joints. And or if it needs to transmit load between layers, it is sufficiently glued, nailed, bolted, whatever it is. So the adding area is probably fine, provided also you've removed all the material which has lost strength. Ideally, you want to make sure the area, so make sure all the area which has lost strength is removed, and then the bonding between the elements is sufficient. So that was where you'd have to be a bit careful. And sometimes you may have to go beyond the damaged area to make sure there's sufficient anchorage between the sections. Okay, then Michael again, is there any research currently underway further investigating charring rates of SA pine in isolation? Now we're waiting for you to pay for that. And then also in engineered wood, the data pool we currently have is small, and more would be very helpful for professionals working in the timber industry. Fire is one of the biggest challenges we face for large-scale adoption of mass timber buildings in South Africa. I think Brunt is smiling right now. Now, are we pursuing timber and fire research? Yes. So we do have projects on the go at the moment. There's a couple. Darren's work may have some results soon. At what rate, it'll depend. So the team is gradually growing. Nothing that's going to be released immediately, but it is something we're hoping to do more and more of assessing these rates. I mean, you're aware we have done paper previously on CLT, looking at fire resistance ratings. More does need to be done in terms of charring and rates, etc. But nothing that we're going to be releasing in the next few months anyway. Okay, then what is the red product coated on trusses and purlins to create fire resistance between housing units, and is it affected? I'm not sure what you mean by the red product. You get your typical iron oxide, which paint, if you're talking about, that's just a primer you put on steel, and that has no fire resistance. That's just a primer. If you are talking specifically in Intumescent, those are what I showed earlier, that it is, where we go. It's one of these products. It has to expand. I've lost my Intumescent. Something like this. A paint alone, it needs to provide a thick char layer. I'll be perfectly honest, even putting this material on a purlin normally doesn't work. Light steel, anything lighter than kind of 4 millimeters. Yeah, you probably can't protect economically with the paint. You normally just allow your purlins to fail. They are thin and they're supporting 0.6 mil sheeting, so the sheeting is going to get stuffed in no time at all. So normally your purlins have 0 fire rating, literally a couple of minutes. So I'd be cautious if someone tells you have fire rated purlins. If you are talking about steel, if you are talking about timber, then I'm not sure. I mean, then you can have products, and that's what we were discussing earlier. You can prevent products that prevent flame spread and slightly increase the resistance, but you have to be cautious of it. Is it effective? Well, it depends what product is being referred to. Any more questions or comments from your side, Brunt?
Yeah, just one more thing. Michael asked about some, if there's enough or more data coming out. There is actually one study that we forgot about, and he's actually he's actually involved in that. So we did test CLT specifically for fire resistance, and we did tests on the different adhesives that you can use, and we also tested a boron product that you can impregnate and see how effective it is in resisting fire. But the results, it's an MSc study, and the results must still be, or the thesis must still be finalized.
I see there's one Is the use of, last question then, is the use of mass timber systems influenced by building type? One thing that does influence it is you have different occupancies, and different occupancies require higher fire ratings or lower fire ratings. So it's firstly based on the number of floors and then also what's in there. If you have a low risk storage versus a high risk storage versus an office versus a prison versus a school, that influences the fire rating and the requirements of the materials. So it's to do with risk and amount of time you want to provide for fire resistance. So that's how the primary resistance comes in. Anyone else want to add anything else to that? Or give link to download handbook. I shall try to do that now. I'm going to stop presenting because that's the only way I'm going to be able to answer that question now. Otherwise, just search this name and it'll pop up as like the first thing. Just search fire safe use of wood in buildings. I'll try to see if I can find it. But or someone who's at a computer, post the download link. I'm managing two screens here. Anyone else want to add in something?
Yes, Richard, one point I want to add is with testing, what we have found is that sometimes people like to take shortcuts, and you ask them, what have you coated the surface of the door? And they would say, no, normal PVA. What we then do is we take the sample and because we have a cone at calorimeter at our advantage, we do some cone tests and you find out that somebody is not talking the truth. So I would recommend people not to take chances with us. We will catch you out. And the cone calorimeter is, I think, most of the valuable pieces of test equipment I've seen around for especially in the timber industry to get proper results and parameters that one, I think, in the past perhaps didn't know or didn't understand what is happening. So yeah, we use that in conjunction with other tests that we do just to make sure sometimes what we see is correct.
Great, thank you all.
Thank you, Richard, and thank you, Dirk, and thank you, Brunt. Really fascinating. I'm glad I'm not an architect or an engineer having to deal with issues like this. We'll leave that to the experts, and really, really thank you for your insights. I am going to hand over to Tafadzwa Nyanzunda from the DTIC. She's a staunch supporter of our work in timber promotion. And just
good afternoon to us all, and I would just like to do a very short thing given our time. Firstly is to thank the audience. I think today was the greatest number that we've recorded. I think over 98 gadgets did log in. Thank you once again for responding to our invitation. And not only did we get many people logging in, there was also a vibrant conversation that happened after the presentation. So once again, thank you. If you did not attend the previous webinars, we will invite you to visit. They are on YouTube and you can actually learn. So we've had people logging in from government, associations, industry, academia. We had quite a lot of people from NHBRC. Thank you once again. Hopefully next time we will have people from municipalities logging in. Great thank you to Sawmilling South Africa for sponsoring this. Sawmilling South Africa, Institute of Timber Construction, and SOPA. Thank you very much once again for the sponsorship. And I would like also to thank the presenters, which is Dirk Streicher and Professor Richard and Professor Brad Wessels, all from the University of Stellenbosch. Thank you once again for accepting the request to do the presentations, as well as facilitation from Prof Brad Wessels. I would like to say thank you to our partners that we are doing the work on the promotion of timber in construction. This is one of the deliverables that is actually in the Forestry Master Plan. So the work that we are doing has been recognized at government level, industry, as well as labor, all documented in the Forestry Master Plan. Once again, thank you all for logging in and for listening to this webinar. Thank you. We look forward to the next webinar. Thank you all.